Okay, guys. In the last class, I have explained the two approaches for estimating the parameter. The one is the frequentist approach, and in this approach, theta is unknown, but it's constant, right? So this is just hidden. And the other approach is Bayesian, and then in this approach, theta is unknown, and also it is taken as the random variable. Okay, so then I'm going to explain more using an example here. Okay, suppose theta is the probability head. Okay, just think of the heads or tails. Okay, costoin. So theta is probability head. This is the parameter we would like to estimate, and then yi is the outcome from the ith costoin. Okay, so then it should be 1 or 0. Okay, the yi is a random variable, and the random variable should be real valued. So head or tail is not a random variable. So this is called random event, right? So then yi is the random variable, and it takes 1 if it's head, and it's 0 if it's tails. Okay, and then suppose we have 10 observations. Okay, you see that 0, 1, 0, 0, 0, 0, 0, 1, 0. So we have 8 zeros and 2 ones, right? And then let's estimate the parameter, the theta, using the frequentist approach. And then you must have heard of maximum likelihood estimation. Okay, and maximum likelihood estimation is just obtain or to get the parameter estimates by literally just maximizing the likelihood. And then to maximize the likelihood, and we should be able to specify the likelihood. Okay, and then as you know, the likelihood is simply the joint density of the observations given the parameter, right? So this is joint density of the y, right? So, and then here you see that these 10 events are independent. So the joint density of y is simply the multiplication of these 10 independent events, right? So then probability of 0, first outcome 0, the y1 equals 0 times the probability that y2 equals 1, because second outcome is 1. Then third is 0, and fourth must be 0, and so forth, right? So we have the 10 likelihood density. And then here, the probability of 0 is what? 1 minus theta, right? And the second outcome is 1. So then probability of 1 is theta. And third outcome is 0, then it should be 1 minus theta, and so forth. So then we have 8 1 minus theta and 2 theta. So it should be theta squared times 1 minus theta to the 8, right? So then this is the likelihood. And then by maximizing this likelihood with respect to theta, we can get the maximum likelihood estimate, right? So then how can we maximize this likelihood function? You can just take the first derivative with respect to theta, or you may want to take log first. And then there should be log likelihood. It should be what? 2 times log theta plus 8 times 1 minus theta. Yeah, either way it should be fine, right? And then you will have theta hat. The maximum likelihood estimates must be 0.2, 20%. It should be 20%. Why? Because 2 outcomes out of 10 experiments are head, right? So then probability head or probability of 1 must be 0.2, right? So this is maximum likelihood estimation, right? So then you see that again. So this is the likelihood, not joint density actually, right? Because this is a function of y or function of theta. It may look like this is function of the y, but actually this is function of theta, because y is what? Y is observations, and so y is fixed, at this particular vector or matrix, right? So you cannot change the y. And then this function value will change to the theta, right? Because you see only theta, so, right? So then if you can put 0.1, 0.6, 0.7, whatever, then this function value will change, and this function value will be maximized at a particular value of theta. The number is 0.2, right? So then 0.2 maximize this likelihood. That means 0.2 maximize the likelihood that 8 outcomes are zeros and 2 outcomes are 1. So then this theta maximize the probability of the y, this y, right? So then according to this maximum likelihood estimation, this 0.2 is the best guess we can have, right? Because this particular value maximize the likelihood that these outcomes can occur, right? Right. So then this parameter maximize this parameter theta hat, 0.2 maximize the likelihood that this particular outcome can be generated from this particular Bernoulli distribution, right? Right. So this is M-array. And now I'm going to explain how to estimate the theta using Bayesian approach. Okay. And then to do this, we need to remind the Bayes rule first. And then this Bayes rule is actually how we think at every moment. Okay. So this is the Bayes rule. You must be aware of very well, right? So then probability A given B equals probability B given A times probability A over probability B. Okay? And here, just look at these two terms, probability A given B and probability A given probability A. What's the difference? Here, in this probability, the B is given, and here, the nothing is given, right? So then B is the new information. So this is probability A without any information. And this is probability of A given new information B. Okay? So then before you observe the B or event B or the whatever, before you have this new information, this is the probability A you think. And then once you have this new information, the probability A can change. You can change your mind, right? And then this, and then here, what is this? The probability B given A, right? So this specifies the relation between A and B. Okay, suppose A and actually you see that this A and B are both random variable, and suppose A and B have no correlation. Okay, there is no relation between A and B. Just A and B are independent. So that means B has no information about A, right? So then probability B given A should be what? Probability B given A should be what? It should be simply probability of B, right? Because whatever A is given or not, okay, it doesn't affect the probability of B, right? So then here's probability of B, here's probability of B. So then these two terms will be cancelled out. So then probability A should be equal to probability A given B, right? So if there is no relation between B and A and B, so then there is no update. Okay, so then again, but in contrast, if A and B are very highly related, then this must be non-zero. So then this value, probability A, should be different from this probability A given B, right? So whenever we have new information at every moment, whenever you watch news or read newspapers, and you can hear you can hear something from your friends, then you will change your mind, right? So these are all new information, and once you have new information, your mind or your expectation will change, or the probability of a particular event will change, right? Because of the new information, right? Okay, right? So then, and then this particular probability is called prior, the prior probability, or just prior. So this is how you thought before the new information is given. Okay, so this is called prior. Okay, and this is the likelihood, the probability B given A. So this is specify the relation between A and B. Okay, okay, and this one is called posterior. So this is prior and this is posterior. So posterior or posterior density, right? So this is literally posterior, because this is posterior probability after the B is observed. So this is also called updated probability. Okay, and then what we are going to do is compute updated probability of theta given what? Given data Y. Because data is the new information. This is new information. And given the new information, we will compute the probability of theta given Y. Okay, this is our Bayesian estimate. Okay, right? Yeah, just move on. Okay, just move on. And then, okay, so again, what is model? Model is always data generating process. Okay, let's understand and let's interpret the model in terms of Bayesian approach. Okay, so here we should be explain how the yi is generated. We should be explain how head or tail is generated randomly. Okay. Okay. For yi to be generated, theta should be given a priori, right? Without theta, we have no idea how yi is generated. Okay. So then yi should be generated given theta. Okay, if theta is high, then the probability of 1 will be high. If theta is low, then probability of 1 will be very low. So the question is, how theta is generated, how theta is given. And we believe that in Bayesian approach, we believe that theta is also random variable. And then because it's random variable, then it should have its own distribution. And my belief, according to my prior belief, according to my prior experience, or just study or literature, okay, according to my prior information, theta is generated from Bayes distribution. Bayes distribution is defined between 0 and 1. Okay, I will explain the details more later. Okay, and then theta is first generated from this Bayes distribution. Then, given this realized theta, then yi is determined. Okay, theta is not necessarily 1/2, because all coins is not necessarily fair. Okay, some coins may not be fair. Okay, probability of 1 could be much higher than 0.5 or lower than 0.5. Right. Okay. Right. So this is how we interpret the model from the Bayesian perspective, right? So then you see that it's very important to note that y and theta are both random variable. These two variables are both random variable. And once you observe the data y, so then which one is no longer random? Y is not random variable anymore, because y are fixed at particular values. Here, y is realized, right? So then observations y is not random variable anymore. So this is just random, non-random, because they are just realizations. And another important point is that y and theta are very highly related, right? Because again, theta is high, then probability of 1 must be very high. So then theta and y are both random variable. And theta and y are very highly related. And by chance, we can observe the realizations of y. So then you should be able to make a better guess about theta using the information in y, right? Okay. So then question is how to update our belief about theta. We can do this using what? Using this Bayes rule. Okay. Okay. Let's do this.